Okay, it's my great pleasure to introduce Daniel Salson. Daniel is a PhD student at Stanford. He's advised by Percy Liang and Davis Dill. Daniel was an intern here last summer. He did a lot of great work on the lean theorem prover. Daniel is interested in both machine learning systems and theorem proving and to check to make sure they work as expected. He's also interested in applying machine learning techniques into theorem proving. And today he's going to present this talk that he presented at ICML.
Thanks, Leo. Hi, everybody. Thanks for coming today. So I'll be presenting a new way to develop bug-free machine learning systems using formal mathematics. And this is all joint work with my two advisors, Percy Liang and David Dill. So here's the problem. It's extremely difficult to detect implementation errors in machine learning systems. If you write a program to sort a list, and the program ever returns an unsorted list, then you know your program has an error, even if you don't detect it when you're writing it. Later on, once it misbehaves, you can detect after the fact that an error has occurred. But if you write a machine learning system, you give it a bunch of data, and the loss function doesn't go down that much. It doesn't work that well. Maybe you just needed more data or more layers, or a different model, or maybe it was just numerically unstable. You don't really know. But maybe the program should work, and it's just a bug in the system. How would you even know? So this is an example recently. So Theano, for those of you who don't know, was the most popular machine learning system for about a decade, and it was notoriously riddled with bugs. Somebody posted an issue about a year ago that they have a model that's training well for about 20 iterations, and then the loss function diverges. And the poster thought that the model should work, and he posted an issue, and the developer said, well, maybe your model is just not supposed to work. How are we supposed to know? And then after doing some experiments and comparing with TensorFlow, a different system where the model behaved similarly for 20 iterations and then continued to go down, the developers finally granted that it probably is a bug, but they don't know where the bug is. They don't know which models are affected. And the scary part is I've given up on models that didn't work well in Theano many times. And I really don't know whether it was just because of a bug or because the model was wrong. There's so many other possible reasons a system can fail that I really don't know whether the model was really at fault. Yeah?
Sorry, memory corruption bug? What kind of bug was it at the end?
They don't know.
They don't know? Because, I mean, we have memory corruption bugs in software for the last 30 years. That's not a new problem.
No,
there are lots of tools to find memory corruption.
That is just the poster's guess for what it was.
Okay.
The developers have no idea whether it was a memory corruption bug or not. Sorry?
No, but that's an interesting story, right? I mean, because again, if it's a memory corruption bug, you should be able to inspect the program and see what it's doing. But you're just saying that what the program is doing is so complicated that the developers who develop Theano, even if they watch what it's doing, they don't know whether it's doing the right thing or not.
Correct.
Okay.
Here's another example. So Hastie and Tibshirani are two famous statisticians. And in 2002, they get very excited about a new method called coordinate descent for the lasso. And they implement it, and they find it works poorly, and they abandon it. But 4 years later, they go to a talk on a similar method that works, and they get excited again. They implement it again and find it state of the art. And they look back, and they realize their original version just had a bug. And they implemented it. It didn't work well. They didn't know if it was supposed to work well. They didn't have math that told them it should work. So they just assumed that the model didn't work well, like most other models. And they actually, how many other great ideas have been abandoned because of bugs? I mean, they actually changed their entire research path because something didn't work that should have worked. So the status quo methodology for software development doesn't work perfectly for regular software, but it really doesn't work for machine learning systems. So the status quo is to test a program empirically, right? You write your program, and then you run the program. And if the program ever does something that you think it shouldn't do, you go back and debug the program and iterate. And sometimes you can release the program, and then users can run it and find bugs, and they can tell you, and this process will iterate. Yeah?
We do more. We write tests. We write regressions. We have specification. It's more than Just like you write it and just let it run. Yeah.
Well, but by let it run, but unit testing is still running.
Yeah.
A lot of testing is still done empirically,
Sure.
based on being able to detect after the fact of an execution that it didn't do what you
And
wanted.
in real numbers, the number of programs that have specifications is 0.
But for memory corruption, there's a very well specification. I mean, you can very precise. So we're waiting to see what kind of properties of program you're talking about here, or in the outside. That's why I'm waiting still here. It's not clear.
We'll go through very
Yeah.
extensive detail, gory detail soon enough.
Okay, go.
Okay, so this doesn't work well for machine learning systems because you don't usually, when it runs, it doesn't work well. You don't actually know that there's a bug. You certainly can't localize it, but you might not even be able to detect a bug. So in our methodology, this won't be new at all to verification people, but we test the program mathematically instead of empirically. So we first formally specify in logic what the program is supposed to do. We write the program, and then we try to prove that the program does what we said it should do. And when the proof gets stuck, every bug in the program will cause the proof to get stuck at some point. And we can look at where the proof got stuck, fix the program accordingly, and iterate. And unlike in the status quo methodology, this loop will eventually terminate with a bug-free system up to your specification and a machine-checkable proof of correctness. So this is probably obvious to the PL people in the room, but I've mostly presented this to machine learning people where this was a very, very wild idea. So how do you specify proof properties of programs? What does it even mean? So it's not possible with traditional programming languages. You can't write down a specification involving integrals and random variables in C. I don't know what that would even mean. You need to somehow jointly reason about programs, theorems, and proofs. And the answer is to use, at least one of the main answers is to use an interactive proof assistant. So it's exactly what they're for, and they've served two communities historically, formal mathematics and software verification, which have had relatively little communication between the two fields. But there have been major successes already in both fields. So in math, they've successfully, actually at MSR, they've successfully formalized what was a 300-page informal proof, all formally. And in software, there's a fully verified C compiler, CompCert, and many, many, many others here and elsewhere. And to prove machine learning systems correct, we actually need to build on both of these fields because we want to be proving properties about specific executable programs, but their semantics involves advanced mathematics and real analysis and integrals and things like that. So in our work, we use the Lean theorem prover, which is developed right here by Leonardo Demura. And before explaining the methodology, we need some background on Lean. This might be familiar to many of you. I'm not sure. So first, basically, it's a functional programming language. You can write functional programs. So here's a function square, takes a number and returns its square. You can state mathematical theorems in a system like Lean. So this is a statement of Fermat's little theorem. And the universal quantifier and the implication arrow are both part of the logic of Lean. So it just already has mathematical semantics analogous to what we're used to in informal math. And you can state theorems about programs also. So the functional programs and the mathematical theorems live in the same universe. So you can state theorems about programs. In this case, we're saying that the program sort always returns a sorted list. And you can prove theorems interactively. And I'll explain this in more detail shortly. We walk through an example. And whenever I say proof, I mean machine-checkable proof. So literally a data structure, some kind of formal certificate that a computer program can check and make sure it actually proves the theorem that's been claimed. So let's walk through a toy example to warm up. So suppose we're trying to compute the gradient of the Softplus function, which is a common function in machine learning. I'll explain what it is in a second. So the first step is to specify what we're trying to implement. So this is the Softplus function, log of 1 plus e to the x. And we want to write a function grad Softplus that takes a real number and gives you a real number. And we're going to leave it as a placeholder for now. And then here's the specification. Grad s plus is correct if for all x, it computes the gradient of the Softplus function at x. Everybody who wants to follow this is following? Okay. So then we program. And I don't remember I don't want to do the derivation by hand. I don't know what the program's supposed to compute. Let's just pretend leaving it as a placeholder is just another bug, and we'll try to fix it through this iterative loop. So now we'll try to prove it correct. So in Lean, when you try to prove something correct, it's an interactive process. At every step, it'll display what the remaining goals are that you need to prove. So in this case, the remaining goal is the statement of the original theorem. And we're trying to prove for all x something, so we're going to introduce x, which is the same as saying let x be an arbitrary real number. and we can then unfold the definition of Softplus to expose the log and the 1 plus e to the x. Then we can just rewrite with exhaustively with known simplification rules for basic gradients. And as a result, the right-hand side will simplify to e to the x over 1 plus e to the x, so our theorem is not true because this doesn't return anything, but it tells us exactly what it needs to return. It needs to return this. So we go back and debug our program, and we fill in what it's supposed to compute, and we go back to proving, and now the same proof goes through, and we're done. Everybody okay with that example?
Simplify grad implemented inside Lean, is it?
Yeah, so Lean has a general purpose simplifier. You just tag a few lemmas as simp rules, and
it knows about gradients and integrals and.
Oh, it does after you have those lemmas and make them as simp rules.
Okay.
It doesn't a priori. Okay,
you made the library for
you need a library, yeah.
for things you need in ML learning.
Exactly.
You made it already, like gradients.
Yeah.
Right. All right.
I'll say a little bit more about that later, but not that much more. So if you want to know how the library is structured, ask me or we can talk offline.
All right.
But I'll tell you a little bit more about that as we go along. So that was a toy example. Let's look at a real example. So as a case study, we used our methodology to build a system called Sertagrad for optimizing over stochastic computation graphs. I'll explain what that means in a second for people who are not in machine learning. So here's some background. So the computation graph is the basic programming abstraction of machine learning, especially of deep learning. And all of the popular systems like TensorFlow and Theano are based on this abstraction. And here's an example. So it's basically just a simple program, usually a directed acyclic graph, where each intermediate node represents some kind of computational operation, like this is matrix multiplication, this is the Softplus function component-wise. And you're going to have some inputs, like the ones in black, that are just data that are fixed, that you know. And you have some inputs, which I put in red, which are parameters that you don't know. And then you have some loss function, which is some notion of how unhappy you are with the parameters at any given stage. So usually if you're doing image recognition, your loss function will be how much probability do you assign to the correct human labels. And the point is that you want to assign more probability to the labels that the humans provided. And then the goal is to find W1 and W2 that will minimize the loss or make the loss small. So the way you do this is by computing gradients. So the main goal of these machine learning systems is to compute the gradient of the loss function with respect to the parameters. And then the standard learning algorithm is called stochastic gradient descent, where basically it's very simple. At every iteration, you have some values of W1 and W2. You compute the gradient of the loss with respect to them, and you take a little step, and then you repeat. And that's basically how deep learning works. So this is a very nice abstraction, but it's reaching its limits. There are lots of new models that are a little too expressive to be supported by computation graphs. So many models require random variables or non-differentiable simulators, especially in reinforcement learning. So Go is not differentiable itself. Go, you have a simulator for Go, but you have a differentiable network spitting out actions that it should take. And you need a way to backpropagate information from the result of the Go game through the network parameters, for example. And the answer is to stochastic computation graphs, which are just computation graphs with random variables. So this is the analog of the example we just saw, where in the middle we throw in a random variable. So we sample a Gaussian with mean, the output of this previous layer of the neural network. And now the loss function is no longer a scalar. It's going to be a random variable itself. So the quantity we're interested in minimizing is the expected value over the random choices in the graph of the loss function nodes. And now the main goal of Sertagrad is to sample unbiased estimates of the gradient of the expected value of the loss with respect to the parameters, because you can no longer do this in closed form in general. So we're actually going to be running a randomized algorithm and only proving properties about it probabilistically. Okay, so let's see how to build Certigrad using our methodology. The first step is to specify what we're trying to build, which I already stated informally, but by analog to the pseudocode, here's the pseudomath. We want to function stochastic backprop such that the expected value of stochastic backprop is the gradient of the expected value of the loss. This is what it means to sample unbiased estimates of the gradient of the expected value of the loss. Now, this might look formal to some people who have no experience with formal reasoning. But it's just LaTeX. It has no semantics. It's just characters. The computer has no idea what expected value means, what a graph is, for example, what gradients are. So in order to use this as a specification for the computer, we need to make it formal. So we need to import libraries for real analysis so that gradient makes sense, for probability so that expected value makes sense. We need to define what a stochastic computation graph on n nodes is. We need to say how a graph and a parameter give you a probability distribution. And then we're going to leave a placeholder for the function we're trying to implement, stochastic backprop. And then the theorem is there's some syntactic clutter, but it's essentially isomorphic to the informal version. We want for all n and for all stochastic computation graphs with n nodes and for all parameters, the expected value over the distribution induced by the graph and the parameter, by sampling, of running stochastic backprop is the gradient of the expected value of the loss function. So it takes a little getting used to the syntax, but it's not, there's no additional complexity here. And unlike this representation here, this actually is in a language with real semantics and the computer can understand and reason about it. So now let's try to program it. And as before, we're going to leave it as a placeholder for now because I have no idea how to write this. There's a lot of tricky cases. What if you have multiple incoming nodes that are some of which are stochastic, some of which aren't, and multiple outgoing nodes, some of which are stochastic, some of which aren't. I don't really want to think about this, so let's just leave this as a bug, and hopefully we can fix it during the proof process. So now we start proving, and we don't actually know anything about G here, so there's nothing we can do, but we can just figure we have to reason by induction. So in this case, in this example, I'm hiding a few details, but the graph is essentially just a list of nodes, where each node has references to the previous nodes in the graph. So it's some topologically sorted set of nodes. And I take a few steps, and then I'm manipulating the right-hand side, and eventually I see that the base case has to be equal to this term, f. So I go back to debug my program, since I've learned something about what it needs to do. And I decide to mirror the induction from before. I'm going to recurse on the graph. And I'm going to fill in the base case as we learned it needs to be. Now I'm going to start proving again. And now I'm in the step case, blah, blah, blah. Oh, but I realized that I hit a proof obligation that some function's integrable. And I can't prove this because I haven't assumed anything about G. So I realized that I actually need to debug my specification. So I go back and add another precondition that some integrals exist on G. And now I go back to prove one more time, take a few more steps, and I massage the right-hand side just enough. I case analysis on whether my node is deterministic or random, and I end up learning that the expected value of S backprop on this branch has to equal this term. And so, as you probably figured out by now, I go back and debug my program. I have the program do case analysis on whether the node is random or deterministic, and I fill in the term. Actually, I mentally figure out something that has the right expectation, which is pretty easy to do locally. And then I fill in that term on the right-hand side, but I still have a placeholder for the random case. And I go back to proving, and suddenly I need to prove something is differentiable. I can't do it. I haven't assumed anything about it, so I go back and debug my specification, and I add a new assumption that all the gradients I need exist. And I try to prove again. I learn something more about the program and debug the program. Try to prove again, missing a precondition, go back to debug my specification. And eventually I try to prove again, prove, and it works. Now, this is great, but the program is wretchedly slow. As a general rule, the programs you synthesize this way by proof-driven development will always be the most naive, most ridiculously slow and stupid programs imaginable. But for those of you who know backpropagation, the key insight to make it efficient is that you need to use dynamic programming. So all we're going to do is memoize this version that we don't need to understand, but we know roughly what the algorithm we're trying to build looks like. So we go back and debug our program, and we rename the backprop that we wrote to slow S backprop. And then we manually, eagerly implement S backprop by memoizing the slow version. And now we only need to prove that S backprop is the same as the slow S backprop. We don't have to reprove the original theorem again. So now we start proving, blah, 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 and we get some goal where you've got some x on the left-hand side, which is supposed to equal some x prime on the right-hand side. This is actually the bug I had I was missing some primes and something. And so we realized that some x was supposed to be an x prime, so we go back and debug our program, replacing x with x prime. We go back to prove, blah, 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 and eventually we're done. And now at this point, congratulations, you really have an efficient and correct program. Now, once we complete the proof, we know that S backprop is correct. We don't need to test it. We don't need to think about edge cases. We don't need to understand how or why it works. The proof assistant absolves us of all of these responsibilities. Now, I can't speak for every software engineer, but I find it extremely stressful having to bear the burden of understanding my own systems and having to think about why they're correct and whether all the invariants are satisfied. I take great comfort in just having this tell me that it's correct and I can sleep easy at night. So we just saw a simplified version. I'll quickly show you a little bit about the complexity that I've hidden. But in the real Sertagrad, every node can be an arbitrarily shaped tensor, not just a real number. And there can be multiple unknown parameters, not just a single parameter theta. But it mostly just complicates the syntax. So for those of you who are curious, here's the actual specification. It looks pretty much, it's much more confusing syntactically, but it's pretty much the same. The expected value of running S backprop is the gradient of the expected value of the loss function. And then you have a couple extra preconditions I didn't mention before. So there's actually quite a bit of complexity hidden in this one. Can differentiate under integrals. So in machine learning papers, if you have a gradient and you have an integral, done. Push the gradient inside the integral. But in mathematics, that's actually not quite so simple. You need smooth first derivatives. Some functions need to be continuous. Something needs to be uniformly integrable. So there's some complexity hidden here. These are pretty simple conditions. And then this is the specification, which really does capture functional correctness for stochastic backprop. OK, so let's talk about actually running Sertagrad. So the program is not executable as is, as was pointed out. It's in terms of infinite precision reals, which are just a mathematical abstraction. So to actually run, we compile the program to bytecode, and we replace reals with floating points. Now, you can introduce numerical instability errors here, but I consider them an orthogonal problem. You can separately verify that your system is numerically stable. There's many different kinds of metrics you can use. But it has nothing to do with the mathematical or algorithmic semantics of your program, which only make sense in terms of reals. So the spec doesn't even make, it's not just that the spec is invalidated when we switch to floating points. The spec doesn't really make sense because integrals, gradients only make sense on real numbers, not on floating points.
And the ML algorithms don't bake in floating point semantics?
No, so TensorFlow, which is Google's machine learning system, will apply algebraic simplifications without any regard for numerical stability. So the only times people in machine learning really care about floating point is in a few of the hard-coded functions require special techniques. So basically, whenever you're computing log sum x, you need to do this trick where you subtract the max first, so you don't get imps. But in general, as a machine learning user level, you just never have floating point issues, at least not that we know of. Or if you do, you get imps and nans. Nobody knows of being burned by silent floating point errors. But I can't actually, I don't know if they have been
What you're
burned.
saying here is that you're not going to discuss about encoding reals as floating points in this work. That's all you're saying.
That's all I'm saying.
We're not saying there's no problem in there.
No, there's a potential problem. I'm just saying it's a different problem.
Okay.
Yeah.
Well, but it could be, you could have a theory of floating points and then
Oh yeah.
have bounds.
So I have abandoned it, but I have a separate project to verify numerical stability of computation graphs. The strategy would be to prove asymptotic backward stability. But I consider it very, very distinct work.
But you think that the proofs are separable, that you won't have to change your proof of correctness when you have a separate proof of numerical.
Absolutely. You end up with two unrelated proofs, that the real version...
That compose with each other.
Yeah. Well, they don't perfectly compose. You have a proof that the real version does what you want in real space, and then you have the proof that the floating point version is faithful to the real version.
So
in that sense, they compose.
I have a quite different question. I wonder if I can pose it now.
Sure.
So when you derive the program, you used certain patterns with memorization. So in some areas of program synthesis are based on the algorithms follow certain designs, divide and conquer or memorization designs. Wondering if you had, if you could say interpose, say, design patterns in the way that you are in your debug.
Yeah. Well, so
in particular, Doug Smith have been pursuing this with kids, orchestral interactive system.
So, yeah, I think they're very compatible. I mean, the main thing that's new here is not really the decomposition patterns, it's the fact that for the individual branches, you can manipulate the proof state to figure out deductively what the program's supposed to do. And it's very compatible with other strategies for...
But you might even put that in this set of systems, that there's a theory of divide and conquer algorithms with equal splitting or less equal splitting or memorization. I wonder if you could interpose that on the proof search process.
Yeah, so let me go back a little. Essentially, when I call that induction tactic at first, that is the dual of saying I want to recurse. So you can imagine tactics that figure out different induction principles to try that would correspond to a program that's, I didn't need that for this work, but that's definitely an interesting direction.
And then in particular, when it comes to machine learning algorithms, I wonder if the algorithms follow, say, a particular pattern of algorithm design. Are they all memorization? Are they all dynamic programming based?
So I think I'll partially answer that as we go along.
Okay.
So the core algorithms in the machine learning, like the systems that people write machine learning programs in, the main algorithm is backpropagation. But the algorithms used in machine learning programs, like specific machine learning programs, are much more varied. And I'll talk about a few examples later on. Where was that? 44? Okay, so in addition to replacing reals with floating points, we're going to replace tensors with an optimized tensor library. So a cute fact about most machine learning systems is that nothing has any impact on performance except matrix multiplication. You spend all your time multiplying huge matrices. So using functional data structures in the interpreter, the compiler, is just completely washed out in the noise. And we can be competitive with the main systems just by wrapping a library for matrix multiplication and convolution and a few other really low-level computations. And then we execute the result in a virtual machine, and as a result, Sertagrad is efficient, as I just said. Even though we use functional data structures and lack some optimizations, it just really doesn't matter. All the time is spent. So GEMM is matrix multiplication. And we're as fast as TensorFlow on CPUs. Now, we could do GPUs also, but we're not proving anything about the devices anyway. So from the perspective of Certigrad, we assume we have an operation matrix multiplication that has the gradient rules that we understand. So we could just as easily wrap a GPU library or a library that can schedule on different devices. So far we've talked about building the core machine learning libraries that compute gradients for all sorts of models. Now let's talk about proving properties of specific machine learning models. So as many of you probably guessed, not all machine learning models have useful specifications. Sometimes they're just heuristics. You're just putting layers here and there and seeing what happens. But many models actually do have useful specifications because they're derived by incrementally improving naive ones using mathematics. So here's an example. This is the naive variational autoencoder. It's the same graph I showed you before. And I'll quickly walk through what this model actually is supposed to do. It's a quite interesting model. You feed in let's just say you're feeding in an image, X, and you're going to apply a little neural network to encode it into a small number of bits. actually floating points between 0 and 1. And then you're going to sample a Gaussian around that as the mean. And then you're going to decode it back to the original high-dimensional space. And then your loss function is going to look at the old x and the reconstructed x and penalize you for the differences. So the goal is to reconstruct x while you have to funnel it through a small number of bits. Now, this is a really nice model intuitively, but it has some problems. So the induced gradient estimator will have very high variance because the actual parameters you're interested in are the random variable appears on the path between this parameter and the loss function. So backpropagation cannot be applied in a straightforward way. So we refine this incrementally. So the first step is to reparameterize the Gaussian. So we first sample a Gaussian from a unit Gaussian, and then we just add the mean to it. And that you can prove that this preserves the expected loss. And then the second transformation is to integrate out the KL divergence. You integrate out parts of the loss function. I'll simplify this a little bit. Some of this loss function, you can actually, the loss is actually going to be some integral over a normal PDF of this stuff. And a lot of this stuff you don't actually need to estimate with samples. You can just compute in closed form analytically. You can solve part of the integral. So we're going to do that here, and we're going to have some of the encoding loss, which can be computed outside of the integral without looking at the sample. And then the decoding loss is the same as before. And now this model is state of the art. This is called the autoencoding variational Bayes model. And you can do some very cool things, which I won't go into. So the status quo is to do pages and pages of tricky math on paper to derive the AEVB. You have to compute all these integrals. You need to justify a bunch of different transformations. And it's quite tricky. But then you usually just implement the AEVB at the end and assume that you did your math right and hope you did your math right. But we can do better. We can encapsulate the derivation steps I showed you as program transformations. And we can prove the program transformations correct once and for all in a library and then apply them automatically to the naive autoencoder or to any other naive model to improve the variance of the gradient estimators. So let's see how to apply our methodology to this problem of writing a program transformation to integrate out the KL divergence. So as always, we start by specifying what we're trying to implement. And here's the placeholder for the, first we're just going to do the computer algebra part. Here's a placeholder for the closed form of the KL divergence, which we don't know what it is yet. I don't want to do the math by hand. And here's the spec that the integral of the Gaussian PDF of this empirical KL divergence actually equals this thing that we were looking for in closed form. And we program as always, and as always, we leave it as a placeholder and see what information we find from the proof process. And we start proving. So we're going to use this calculational environment, which lets us state the intermediate steps of the proof and justify them as we go along. So first we're going to unfold the definition of the empirical KL to expose these log PDFs. And we just keep going as if we were doing a derivation by hand, but with some of the steps automated or justified. And eventually we realize we need sigma greater than 0 to apply some lemma. So we realize that our theorem is actually wrong, so we debug our specification, add an extra precondition, sigma greater than 0, go back to proving, step, step, step. And eventually we're going to actually come up with something in closed form that we can use as the result of the program we're looking for. So this theorem is still not true because this is just a placeholder. But we go back and debug our program and fill in the value we computed. And we start proving again, and this time the proof goes through and we're done. Now we still need to write the graph transformation itself. This was just the mathematical justification. But it's routine. I mean, there's no way to make a mistake, so we don't really have to think that hard. Pretty much just keep turning the crank without a care in the world. And with that, I'll try to start wrapping up. So it's hard to build machine learning systems, even when they don't need to be perfect. So an interactive proof assistant can make the process easier, not just facilitate perfect code or bug-free code in the limit of developer effort, but it can actually make the process easier in many ways. So it can help you find bugs, as we saw. It can do algebra for you. It can partially synthesize program fragments or let you figure out what programs need to return in various branches. And most importantly, it reduces the overall cognitive demand because you just don't need to be constantly worrying about whether all the little parts of your system line up and match up and whether it actually does something mathematically meaningful. And as a general principle, the more precisely you state your goal, the more a computer can help. And once we write a functional correctness specification, in principle, it can build your entire system for you. I mean, it's a little far-fetched, but not that far-fetched to automate this iterative process I've just been describing. We're not there yet, but in principle, there's potentially a path to full large-scale system program synthesis using this interactive process. And a really important note is that our methodology can be adopted incrementally. So not all code fragments need specifications. You can have large parts of your system where you don't prove anything about it. Even once you state your lemmas and theorems, you can use them just as documentation, just to get clarity and only prove some parts of it and leave other things that you think are probably true unproven. And just like we wrapped eigen for tensor operations, you can wrap a lot of existing code. So if you really only cared about verifying state-of-the-art machine learning programs, you could wrap all of TensorFlow, for example. Just give it some axioms and then prove properties about TensorFlow programs. And I actually, overall, this methodology is right now still substantially more work than just writing it, especially if you don't care about it being correct. You're willing to tolerate silent failures. But I'd say I got the vast majority of the benefit of these benefits, especially reduced cognitive demand, way before I had verified the system. I mean, I finished the system with extremely high confidence it was correct, just from the functional correctness spec without the preconditions, with sorries everywhere, with some obvious lemmas with no proofs. You really get the vast majority of the benefits for just a tiny fraction of the work. And then all of the extra effort that makes it not economical doesn't really add all that much to the overall trustworthiness of the system. So I think if this methodology were adopted, I would hope people would not feel burdened by the expectation of full purity. Yes?
So the methodology you described in the slides of synthesizing the code from the process of generating the proof, is that really the way you build it? I mean, because it seems like the same paper from which you get the spec, or the same chapter in an ML textbook from which you get the spec, will also provide you the program that you need to use. So why not just start with that?
Maybe in some cases, I didn't find one for stochastic computation graphs. The pseudocode was very confusing. Sometimes, if you have really good pseudocode, you could just write it and then just use this to fix the errors. Sometimes you actually know, sometimes the pseudocode really comes later. You know mathematically what you want an algorithm to do. Like in this case, the spec is one line. Unbiased estimate, gradient of the expected loss. And then the algorithm, it depends on implementation details of your graph. So
it's interesting because I would think that ML, the ML community would be a lot more, would be a community where you could very easily get pseudocode and algorithms, but it was hard to get specs. And you're saying it's the other way around, that it's easy to get specs, it's hard to get pseudocode.
Well, I think it depends. I mean, the examples I chose happen to have great simple specs. There's always a counterexample of something that is some simple procedure heuristic that does not have an interesting spec. But there are a lot of important problems where the spec is much simpler than the program. So I'll just leave it at that for now. And also, it's not, this synthesis thing isn't there are limits to it. I mean, it didn't find the memoization, for example. It synthesized a very stupid version. So you still need some insight and you need to be willing to figure out how to write a program, or else you might hit a brick wall. But you often get a lot of useful information from the proof process itself. Yeah?
Yes, my question is related to this memoization thing, especially like I think a lot of bugs come in when programmers try to do complex like performance optimizations where you think you have this like property and you like code up something that is like really complex, which seems like it's working correctly for a bunch of cases. Like I think asynchrony is one of these things, like reduced precision in a lot of these new machine learning models is one of these things. Is there any way to comment about those things where you don't get perfectly the same program? Like
so reduced precision, what you'd want to prove is something on the floating point side. You'd want to prove that for specific programs, your error is still bounded by something reasonable.
Right, but it's actually not the floating point error. In some sense, the reduced precision systems admit there's floating point error, but the fact that it doesn't affect the optimization or the generalization errors that you're seeing is their claim, if my understanding is correct.
Well, part of the claim.
So this sort of relates back to the composing the two groups in some sense, in the sense that is there any way to comment on things that are known to be approximations? That's what I'm hinting at. And the answer could be no, that we don't have ways to reason about those things yet. But
So, I think the general answer is it's a case-by-case thing. So for these graphs, you can do additional transformations that introduce bias to your estimator, but will lower the variance. And you can prove that you'll have lower variance, even though you no longer are unbiased. So you have to switch spec to prove the property that you care about, given your approximation trade-offs.
okay.
Yeah, I think it's case by case. There are many cases where some approximation will have a spec that's meaningful and useful, and some cases where it really is just, I think this will work better, and there's no mathematical justification. Yes?
I have a question. This is really cool work. I love
Thanks.
it. I'm thinking, you're saying that TensorFlow applies a lot of computer algebra optimizations to their graph representation. Could you hook this up to TensorFlow so that you kind of validate the transformations that it does or detect
Well,
errors?
this is, it's not professional like TensorFlow, but it is a TensorFlow competitor in that sense.
I understand
it
that.
does what TensorFlow does.
Yeah, but lots of people use TensorFlow, and if
Yeah.
it makes errors along the way, then if you hook this up as a validator, you detect those errors.
So if there are a lot of bugs in TensorFlow.
Then you find lots of bugs.
So most of the bugs that I'm aware of are in gradients of complicated functions, which you could use a tool like Lean to derive mathematically and then implement in C++. So a lot of the errors there are on the math side, not just the implementation, but they've derived some of the things wrong. And then another source of errors, I would presume, at least this was a source of errors in Theano, an older system, was not the algebraic optimizations in the compiler, but optimizations saying okay, this update can be in place. This update can be in place. There are lots of things like that that are further separated from the math, that are more like normal compiler optimizations. The short answer is maybe. The hardest part would just be connecting the C++ code that they're writing with anything that has a mathematical meaning. You can certainly verify the pseudocode of TensorFlow and then implement it.
It sounds like TensorFlow, does TensorFlow take a graph and then try to apply a series of optimizations, sort of people optimizations to simplify it, to make it more efficient?
Yes.
Okay, so that sort of thing, because Nuno Lopez does this amazing stuff, where he takes LLVM and it does a whole lot of transformations on the sort of people optimizations on the micro. It's got nothing to do with machine learning, but then he finds bugs in the course of doing that. And so I'm just thinking about
I bet
because it's going to take a long time to get a lot of people to use your system, I would guess. Because
I'm not planning to compete with TensorFlow here. This is a research prototype.
Sure.
Yeah, I think there probably have a ton of bugs in the TensorFlow optimizing compiler that have not even been discovered yet. I think that's people looking for a bug hunt where people would care about bugs. I think that's a great target, and a lot of them won't require the formal mathematics. A lot of the errors are just going to be normal compiler errors. Some of them will require the formal mathematics, but not all of them. Yeah.
On your conclusion slide at the very top, you had ML systems do not need to be perfect. Not sure. So how you say that TensorFlow has lots of bugs. How severe are those bugs? I mean, there's so many known when you apply this stuff. Basically, there's no overall specification in any case. So how important is verification in that space really? And what kind of verification is important?
So I think the worst thing that can happen. So right now, we're still in the early stages of machine learning where most training is done offline. So I'll train my system offline, and I'll only deploy it if it's learned something from the data and it works well on my test set. So in that scenario, it's not really about safety critical systems, because if it's trained well and it works well already, then you can probably deploy it, and none of the bugs that affected training are going to leak into deployment.
And you fix your bugs, you may not get the right model that you wanted in the first place, right?
Oh, yeah, so you can still have the wrong model.
So in some sense, whatever, if you get a good result, a good model of your training set, problem solved. You don't care whether there are bugs underneath.
Well, so there's two issues, though. The main thing, as I pointed out in the beginning with the example of the statisticians, is that the models that have already been scaled up and are deployed for vision, for translation, those models don't have bugs.
Well,
Or they don't have major bugs.
well,
But, or they work despite the possibility of having bugs.
yeah, because they're bug tolerant. It doesn't matter. How you got
I don't
the
think there's
model,
evidence that
when you get at the end, what you get the model at the end is the result that matters, not
Yeah,
how you got.
I agree.
Okay.
The problem is when you're experimenting with a new kind of model and it doesn't work,
Yeah.
and you don't get the results.
Yeah.
Then, if that's because of a bug, and the
But
entire...
there could be many different reasons, perhaps a bug in the implementation. Wonder how often it is, or because you just not the knobs the wrong way.
It's
you
more
pick up the
often
wrong
the
library, you pick the wrong algorithm, you have the wrong training set, and that's the huge mess that we're in right now.
I agree
Nobody
completely.
knows.
Most of the time, it's not because of an implementation bug. It's just especially tragic and preventable when an entire field abandons a line of research because of an implementation bug. But the other answer is that we're not far from the world where systems are actually learning from data in deployment. So right now we have this two-stage system where you train, you get something that works well, and then you deploy. But once you have models that are learning on the fly, you don't want them to fail to learn. It could actually become a safety critical issue if they fail to learn things that you know empirically they should learn on similar things, but they fail to learn from this new kind of data.
And don't get me wrong, I don't want to, this is very interesting, but like your 4 bullets there, how find bugs, that's algebra track. We'd love in the years to come to get more and more evidence that this is really true. We have not much evidence of that today. So this is an interesting research program, early work, continue, but I'm not convinced that this is moving the needle on those.
So just to clarify, I'm not saying that this methodology...
That's why I'm adamant about this,
Yeah.
to make sure you agree with me or not, or where is the evidence?
So just to clarify what I'm claiming here, I'm not claiming that this methodology will help you find bugs in TensorFlow. You asked about that. That's a separate problem as far as I'm concerned. I'm saying if you are using this methodology, it absolutely helps you find bugs because you can't finish your proof.
Yes, but Andy suggested that you should use your system with TensorFlow in order to find bugs in TensorFlow.
Wait, can you say that more slowly?
Isn't it? Andy was suggesting that you use your methodology and try to look at TensorFlow to find bugs in TensorFlow.
Yeah, if I wrote the TensorFlow algorithms in this system, in this methodology, and there were bugs, I would absolutely find them.
Yes.
But it's not an automatic tool that's going to point at TensorFlow.
Yeah. That was suggested, right?
Yeah.
So that's, I think that's good suggestion.
That's a great suggestion. I agree.
You will get much more attention, and then you get more result, concrete evidence for the first bullet, for instance. For me, skeptic.
And the first class of bugs I would get is the gradient calculations for the individual kernels in TensorFlow, because that's something that would be fairly easy to automate the derivations of in Lean. So that might be close to free.
Right, and I was thinking as a reverse thing, which is that this incremental point is probably really interesting in the sense that you're making this point that there are bugs at various levels, right? You sometimes have bad linear algebra operators, you sometimes have like bad, network specifications, and then you sometimes have just the wrong data, wrong model, and so on. And I think the way I look at it is that what you're trying to say here is we can build more better building blocks underneath these layers, and if you're doing something at a higher level, then at least the lower levels are correct.
Yeah. Here's a summary image. You have a system, it does something stupid, you have a big checklist, lots of possible what went wrongs, and there's just one thing is crossed out. From a safety perspective, that's all I'm claiming. Your system will still go wrong forever for any number of reasons. Yeah.
If you wanted to use this methodology to find a bug in an existing piece of code like TensorFlow, wouldn't you need the ability to synthesize a counterexample? Because you could your methodology allows you to take a buggy program and turn it into a correct program, but it doesn't let you demonstrate to somebody that a buggy program is buggy unless you could generate counterexamples. Like, here's an input, look and see the gradient is wrong. How could you synthesize a counterexample?
Well, sometimes the way it finds bugs will point at a counterexample. Let me go back. A lot of slides. So this case, I get to some goal where x is x on one side and x prime on the other side. It's pretty easy to go from that to say, okay, I find them in the program, and then I enter it different from the other value, and I can construct a counterexample. That doesn't always work like that. But often the information you learn about the program when the proof fails indicates what the counterexample would need to look like.
Another one would be where you said you should be able to differentiate under the integral. Like you made.
Those counterexamples are way more complicated.
Well, it's a
you have to construct some crazy thing.
Right. Or the sigma bigger than 0, maybe you can make one that's not, right?
Yeah, that's a good example.
Yeah.
Fun. So is this your PC project?
No. Oh, this specifically is not. Follow-up work might be.
But you're still working on her. Awesome.
Thanks. Oh, that was my last slide. Okay. Great.